For the fifth year running, Scan AI is proud to support FDL Europe and the Earth Systems Lab 2024 research event. In this video, we'll take a look at the initial results of this year's 4 research projects. But before we do, it's worth reiterating that the goal of FDL Europe is to explore new science and techniques in a safe, ethical and reproducible way to the biggest challenges in space science and exploration for the good of all humankind. FDL Europe Earth Systems Lab 2024 is a collaboration between the European Space Agency and Trillium technologies. Industry partners including NVIDIA and Scan, plus a wide range of research and technology organisations.
Clouds reflect solar radiation back into space. They also trap infrared radiation emitted under the clouds. 2 competing effects that are the biggest source of uncertainty in predictions of our future climate. The radiation balance depends on many factors, including the 3-dimensional structures of clouds throughout the atmosphere, which is not easy to measure on a global scale. ESA's and JAXA's new EarthCare mission was successfully launched on the 28th of May 2024 and will use LiDAR, radar, a multispectral imager and a broadband radiometer to assemble a 3D snapshot of the atmosphere along narrow tracks. However, this strip represents only a small fraction of the atmosphere compared to the 2D imagery acquired every day by satellites in geostationary and low Earth orbit. The 3D Clouds team aims to use machine learning and multiple 2D images to reconstruct the 3-dimensional cloud structure beyond the narrow tracks, ultimately providing a robust model of our atmosphere over long timescales to better understand our future climate.
The first challenge saw the 3D Clouds team look to combine the 2D data sets from multiple satellites to derive 3D information and create flexible models that are input sensor agnostic and able to translate different 2D sensors to 3D profiles.
Along the satellite tracks, we have satellite imagery and vertical profiles, which can be used to answer the question, if a cloud has a given spatial pattern, what does its vertical profile look like? For this, we have gigabytes of image profile pairs that can be used to train AI models. Off-track, we have only satellite images. These could potentially be used to learn more generally about cloud behavior. In this case, we have much more data, in the order of 1,000 times more. So how can we combine the small specialized dataset and the large general-purpose dataset in order to get high-quality 3D cloud maps? Our NEFOS methodology is a 2-step approach where, in a first so-called pre-training step, we use the large dataset of satellite imagery to learn generally about cloud behavior. And in a second so-called fine-tuning step, we use the smaller dataset to specialize the model's knowledge of what a cloud's vertical profile is based on its spatial pattern. In the first pre-training step, using the large dataset, we develop a model that learns general cloud behavior by using the self-supervision trick. This trick involves pairing each image in our large dataset with a masked version of itself.
Not only were the results from the new model more accurate than current solutions, but the team was also able to create global cloud maps for anywhere in the world using satellite data readily available every 15 minutes. This new tool will form a basis to advance climate science via 3D cloud data.
Forests are some of the most precious and diverse ecosystems on the planet, with tropical forests hosting around half of all known species. Forests also store enormous amounts of carbon, locked away in trunks and branches as biomass. It is essential that we measure the volume and health of our forests worldwide and continue to update our knowledge as our climate changes. In 2025, ESA will launch the Biomass mission, equipped with a world-first orbital P-band synthetic aperture radar instrument to continually map our forests on a planetary scale. The FDL Europe team this year have developed new machine learning workflows that rapidly produce accurate maps of forest structure in 3 dimensions, leading to trusted measurements of our forest ecosystem over time.
In the second challenge, the research team used synthetic aperture radar captured by planes to record forest coverage and biomass data below the canopy. These 2D SAR images were then combined into stacks to result in a 3D tomographic reconstruction of the scene.
I'm now going to show you our classification model results. In the moving image, you're able to see the different dominant tree species in different colors as results of our model, combined with our height estimation. For the classification model, we obtain an overall accuracy of 75%, which is quite good considering that we're estimating 8 different classes of forests. The model performs better on certain species of trees than others due to data availability. We're now going to show you the results for our height estimation model. We ran the model for each forest type, and you can see that the errors that we get for each class differ based on the data availability. But we still get an overall mean absolute error of about 1.5 meters, with most trees being around 20 meters high. The right bottom map shows the ground truth and the prediction results, and you can see that there is a very good match. The final part of our challenge was to work with the SAR images directly to see if we could recreate the forest heights without the tomographic processing. Our initial results show that high reconstruction is possible, although the high prediction is less accurate than using the tomographic data directly.
The model was able to accurately predict forest biomass height and tree type. Therefore, the algorithm will be shared to support the European Space Agency biomass mission, providing generalization for global biodiversity mapping and potential forest monitoring when combined with time series data.
Space technologies are delivering greater value to a more diverse set of stakeholders than ever before. Earth observation data especially can deliver great value in diverse applications such as environmental monitoring, critical infrastructure surveillance, flood mapping, or maritime surveillance. These models could be a game changer, particularly for synthetic aperture radar data users, as the complexity of SAR makes it difficult to apply analytical processes consistently across different locations and times. Building on their work from 2023, the FDL Europe Challenge aims to further refine the best practices in constructing such a scientific SAR foundation model. It is anticipated to have a substantial impact, unlocking numerous applications, particularly in nighttime, in areas obscured by clouds, and to assess the impact during natural disasters such as flooding.
Building on last year's research, the SAR-FM team wanted to develop a foundation model for synthetic aperture radar applications. Maestro was developed to assess whether models could accurately identify land from water, tree coverage, buildings, or the exact location of items.
Finally, we have performed more than 2,000 experiments in 35 testing regions. We used 8 state-of-the-art foundation models from NASA, Clay, BiggerSnap, and of course FDL. We also built a segmentation probe of Maestro based on a wonderful library called Segmentation Models PyTorch, which allowed us to use more than 500 encoders, 9 segmentation decoders for those experiments. And as for board floods, it is a well-polished dataset consistent with 12,000 images, including the Luxembourg. It is an end-to-end pipeline with 8 currently foundation models that we can use for flood mapping, among other things. Finally, yes, our future work would be to add even more foundation models.
The team used Maestro to develop a new foundation model called World Flood SAR, which includes all the necessary images and datasets to provide accurate flood prediction.
The activity on our nearest star is increasing as we approach the maximum in its 11-year cycle. We are seeing more sunspots, flares, and coronal mass ejections that can affect the Earth, leading to spectacular aurora like those seen worldwide in early June 2024. But solar weather can also be dangerous, causing power surges in electrical power grids, damaging satellites through particle bombardment, and exposing pilots and astronauts to high doses of radiation. We need better solar weather forecasts and better warning systems. The upcoming ESA Vigil mission to the 5th Lagrange point will provide an unprecedented early view of the Sun before it rotates towards the Earth. This year, the FDL Solar Eruptions team is providing an early warning system for predicting solar eruptions based on a combination of multimodal data from solar observing satellites, including Vigil. This work has the potential to fundamentally improve the capabilities of our space weather forecasting system for the benefit of the entire planet.
The solar eruption team had a particularly difficult challenge, seeking to discover if there were any correlations hidden in the limited data available on solar flare and coronal mass ejections that could act as a precursor to solar flares. Early predictions of activity are limited by the Sun's rotation, but the Vigil missions will change this, as we'll get a view of the Sun up to 5 days ahead of what we normally see from Earth.
This video illustrates the unique vantage point of the Vigil mission. Vigil's position offers us a side view of the Sun, a perspective that has previously only been possible when another spacecraft happened to be in the right place at the right time. This optimal position allows us to observe solar activities before they rotate into the Earth's field of view.
The other key challenge was accuracy of prediction, as turning off expensive infrastructure to avoid damage would be costly if no solar event occurred. The team proposed HelioWatch, a modular framework for solar flare prediction.
Now I'm going to present you a demo of our results. We have developed a pipeline that is able to take in various different data sources as an input. On top of that, we can also plug in different models for training. Essentially, there are 3 outputs that we can learn out of our pipeline: the most informing inputs, the lead time in hours, and the accuracy of our predictions compared to other baselines and true values. So we are not only developing more reliable forecasting models, we are also gaining deeper insights into the fundamental physics of the Sun's behavior. In this plot at the bottom, it shows how the true label changes with respect to the date. 0 means no flare and 1 means flare. Following the standard practice, as I mentioned before, the label is as well 1 for 24 hours before the actual flare. Stars denote the flares. The vertical dashed line shows the time at which the magnetogram images above were taken. And now we compare our predictions in blue. We show our prediction accuracy in terms of probability. We can see that from October 19 to 20, our prediction in blue rises as we approach the actual flare, denoted by the first star. For the second and third stars, which indicate the other flares, the model has accurately predicted even up to a day in advance. These initial results have provided us a lot of insights, and certainly there is still room to improve.
As you can see, encouraging results there, and as Vigil isn't expected to launch until 2031, the team have some time to keep improving their model's accuracy. And this brings us to the end of our roundup of the FDL 2024 showcase. The link to the complete live stream is included in the description below, along with links to case studies from previous year's FDL research sprints. Don't forget to look out for the full case studies of these challenges later in the year.